morning, and happy Thursday or Friday, whichever the case may be. Actually, no, I'm kidding. Happy Monday or Tuesday. Um, and it's a long day, a lot of days before that when I'm recording this. All right, so we're gonna talk today about conditional statements and then touch a little bit on some postulates and theorems of geometry, which relate back to what we did last time as well. So first of all, some vocabulary, some terminology. We, if we talk about inductive reasoning is known as a form of reasoning in which a conclusion is raised based on a pattern present in numerous or even individual observations. We look for a pattern or a trend. A lot of times I also say this is anecdotal. An anecdote is a story that is told. Well, if we look at just that story and expand that to the larger scenario. So examples of inductive reasoning. Um, Michael just moved here from Chicago, and Michael has red hair. Therefore, everyone from Chicago has red hair. Well, that may or may not be true, right? Um, Second example of inductive reasoning. The children in that house yell loudly when they play in their bedroom. I can hear children yelling in that house, therefore the children must be playing in their bedroom. Okay, so we know that sometimes they yell when they're in their bedroom. So if I hear them yelling, I'm concluding they're in their bedroom. May or may not be true. So inductive reasoning can sometimes be true. If you have a preponderance of data and you're able to make a valid conclusion from it, then inductive reasoning can be helpful. But inductive reasoning is not dependable in that you may not have enough information to make a valid conclusion. Um, so, uh, all right. What is always dependable, however, is deductive reasoning. Deductive reasoning is a form of reasoning where the conclusion is based off of facts that are observed and are verified to be true. Start with just the facts and deduce other facts, therefore, that you know are true. And the most famous person in literature that's known for deductive reasoning is Sherlock Holmes. And at the end of every Sherlock Holmes case, famously, he always says, well, it's elementary, my dear Watson, and that there's only one possibility remaining. We've considered everything, we've analyzed all the facts, so the only thing that could be true is just how it happened, based on all of our observations. So deductive reasoning is something where you look at the facts and you are only led to the conclusions that the facts allow you to do. It's what investigators do. It's how we establish proofs in geometry and math, how we prove something to be true. So on we go. We know that a conjecture, we talked about it before, it's an educated guess, a conclusion based on the information. So the conjecture in each case, if I tell you that A times B equals 0, then what you know to be true based on mathematical facts is that either A or B must be equal to 0. Because the only way you can multiply two numbers together and have their product be 0 is that if one of the two numbers is 0. Secondly, if I talk about the sum of two odd numbers, and we talked about this last time, anytime I add two odd numbers together, I always get an even number. So no matter what the odd numbers are, my conjecture is that their sum will be even numbers. And again, a counterexample is something that shows a statement to be false. All right, so if the statement was no triangles have two sides of the same length, you could say that is false because isosceles triangles have two sides the same length, and the third side may or may not be the same length. All basketball players are more than 6 feet tall. That is false because back in my day, there was a player named Spud Webb who was 5'4", and he won the slam dunk championship. He could really freaking jump. So all basketball players are not more than 6 feet tall. Finally, we talk about conditional statements. Conditional statements are always organized as if P, then Q. So there's a hypothesis, that is the P part, so if something, and then there's the conclusion, that's the Q part, doesn't include the then. So my example of a conditional statement is that if 5x equals 10, then x equals 2. Okay, so 5x plus 10, my P here is 5x plus 10, and my Q is x equals 2. So we can also make those negative to add not or remove not. So example, I could say if 5x is not equal to 10, then x is not equal to 2. So that's how I would make that statement negative. So an example here, another one. If you are in math class, so there's my P, then you need a pencil. There's my Q. So this is P and this is Q. Versus if you are not in math class, then you do not need a pencil. So there's it made negative. So that's conditional statements. Let's look a little more on the next page. All right. So we have we talk about a conditional and a converse. So a converse is that if you switch the Q and P, so you put Q and then P together, Q and P in opposite places. So an example, if my P and Q, P is I'm alive, Q is I am breathing, then the conditional is if I am alive, then I am breathing. The converse to that is if I am breathing, then I am alive. All right. Now, either or both or neither of the conditional and the converse may be true. So if we consider the conditional, if I'm alive, then I am breathing, is that always true? Well, can you come up with a counterexample of when that would not be true? Well, yes. How about when you're holding your breath? If you're holding your breath, you are alive, but you are not breathing, right? Now, what about the converse? Is the converse always true? If I am breathing, then I am alive. Well, yeah, that one is true because if you're breathing, then that you have to be alive in order to breathe. So if you're breathing, that's a test to know that you're alive. So there we go. Next example, shape has four sides. So if it has four sides, then it's rectangle. And I'm kind of leaving some words out here so fit it in the space. If a shape has four sides, then it's a rectangle. Is that always true? Well, no, it's not, because this four-sided shape could be just a quadrilateral, could be a trapezoid, could be a parallelogram, could be a lot of things besides a rectangle. But if we consider the converse, if it is a rectangle, then it has four sides. That is true because every rectangle has four sides. So if we know it's a rectangle, then it has four sides. All right, let's look at the last one. If lines intersect at 90 degrees, then lines are perpendicular. So if lines intersect at 90 degrees, then the lines are perpendicular. The converse is if lines are perpendicular, then they intersect at 90 degrees. All right. In this case, they are both true. If lines intersect at 90 degrees, then they're perpendicular. Yes. If they're perpendicular, then they intersect at 90 degrees. This is what's known when it goes both ways. This is what's known as a biconditional. All right. If both the conditional and the converse are true, then it's called a biconditional. A lot of terminology here today. I know it stinks, but gotta keep up with it. You're gonna need to know these terms, conditional and converse, if P then Q. I would suggest, or we'll provide you a little crib sheet on all of them. There's also inverse and contrapositive when we do them another way around. So you'll be able to remember which one is which. It's more important to know the logic of how it works rather than memorizing QP is converse and PQ is conditional. It's more important to know how it works. All right. So that's the stuff on conditionals for day one. I'm going to create another notes that will be on how that applies to parallel lines and transversals for